Section 1 of Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in April 2010. Histology of the Blood, Normal and Pathological, by P. Ehrlich and A. Lazarus. Edited and translated by W. Myers, M.A., M.B., B.Sc., John Lucas Walker Student of Pathology. With a preface by J. Sims Woodhead, M.D., Professor of Pathology in the University of Cambridge. Preface. In no department of pathology has advance been so fitful and interrupted as in that dealing with blood changes in various forms of disease, though none now offers a field that promises such an abundant return for an equal expenditure of time and labor. Observations of great importance were early made by Wharton Jones, Waller, and Hugues Bennett in this country, and by Virchow and Max Schulze in Germany. Not, however, until the decade ending in 1890 was it realized what a large amount of new work on the corpuscular elements of the blood had been done by Hayem and by Ehrlich and his pupils. As successive papers were published, especially from German laboratories, it became evident that the systematic study of the blood by various new methods was resulting in the acquisition of a large number of facts bearing on the pathology of the blood, though it was still difficult to localize many of the normal hematogenic processes. The production of the various cells and the pathological conditions, where so many new factors are introduced, must necessarily be enshrouded in even greater obscurity and could only be accurately determined by patient investigation, a careful arrangement and study of facts, and cautious deduction from accumulated and classified observations. The pathology of the blood, especially of the corpuscular elements, though one of the most interesting, is certainly one of the most confusing of all departments of pathology, and to those who have not given almost undivided attention to this subject, it is extremely difficult to obtain a comprehensive and accurate view of the blood in disease. It is for this reason that we welcome the present work in its English garb. Professor Ehrlich, by his careful and extended observations on the blood, has qualified himself to give a bird's-eye view of the subject, such as few, if any, are capable of offering, and his book, now so well translated by Mr. Myers, must remain one of the classical works on blood in disease and on blood diseases, and in introducing it to English readers, Mr. Myers makes an important contribution to the accurate study of hemopathology in this country. Comparatively few amongst us are able to make a cytological examination of the blood, whilst fewer still are competent to interpret the results of such an examination. How many of our physicians are in a position to distinguish between a myelogenic leukocythemia and a lymphatic leukemia? How many of us could draw correct inferences from the fact that in typhoid fever there may not only be no increase in the number of certain of the white cells of the blood, but an actual leukopenia? How many appreciated the diagnostic value of the difference in the cellular elements in the blood in cases of scarlet fever and of measles, and how many have anything more than a general idea as to the significance of a hypoleukocytosis or a hyperleukocytosis in a case of acute pneumonia, or as to the relations of cells of different forms, and the percentage quantity of hemoglobin found in the various types of anemia? One of the most important points indicated in the following pages is that the cellular elements of the blood must be studied as a whole and not as isolated factors, as, "It has always been shown that the character of a leukemic condition is only settled by a concurrence of a large number of single symptoms, of which each one is indispensable for the diagnosis, and which taken together are absolutely conclusive." Conditions of experiment can of course be carefully determined, so far at any rate as the introduction of substances from outside is concerned, But we must always bear in mind that it is impossible, except in very special cases of disease, to separate the action of the bone marrow from the action of the lymphatic glands. Still, by careful observation, and in special cases, especially when the various organs and parts may be examined after death, information may be gained even on this point. By means of experiment, the production of leukocytosis by peptones, the action of microorganisms on the bone marrow, the influence of the products of decaying or degenerating epithelial or endothelioid cells may all be studied in a more or less perfect form, but, withal, it is only by a study of the numerous conditions under which alterations in the cellular elements take place in the blood that any accurate information can be obtained. Hence, for further knowledge of the structure and certain functions of the blood, we must to a great extent rely upon clinical observation. Some of the simpler problems have already been flooded with light by those who, following in Ehrlich's footsteps, have studied the blood in disease. But many of even greater importance might be cited from the work before us. With the abundant information, the well-argued deductions, and the carefully drawn-up statement here placed before us, it may be claimed that we are now in a position to make diagnoses that not long ago were quite beyond our reach, whilst the thorough training of our younger medical men in the methods of blood examination must result in the accumulation of new facts of prime importance both to the pathologist and to the physician. Both teacher and investigator cannot but feel that they have now at command not only accurate results obtained by careful observation, but the foundation on which the superstructure has been built up, exquisite but simple methods of research. Ehrlich's methods may be, and have already been, somewhat modified as occasion requires, but the principles of fixation and staining here set forth must for long remain the methods to be utilized in future work. His differential staining, in which he utilized the special affinities that certain cells and parts of cells have for basic, acid, and neutral stains, was simply a foreshadowing of his work on the affinity that certain cells and tissues have for specific drugs and toxins. The study of these special elective affinities now forms a very wide field of investigation in which numerous workers are already engaged in determining the position and nature of these seeds of election for special proteid and other poisons. The researches of Metchnikoff, of Kantak and Hardy, of Meyer, of Buchanan, and others, are supplementary and complementary to those carried out in the German school, but we may safely say that this work must be looked upon as influencing the study of blood more than any that has yet been published. It is only after a careful study of this book that any idea of the enormous amount of work that has been contributed to hematology by Ehrlich and his pupils, and the relatively important part that such a work must play in guiding and encouraging those who are interested in this fascinating subject, can be formed. The translation appears to have been very carefully made, and the opportunity has been seized to add notes on certain points that have a special bearing on Ehrlich's work, or that have been brought into prominence since the time that the original work was produced. This renders the English edition in certain respects superior even to the original. G. Sims Woodhead. Note by the translator. This translation of the first part of Die Anämie, Notnagels spezielle Pathologie und Therapie, Volume 8, was carried out under the personal guidance of Professor Ehrlich. Several alterations and additions have been made in the present edition. To my friend Dr. Cobbett I owe a debt of gratitude for his kind help in the revision of the proof sheets. W.M. End of section 1. Of Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Avai in May 2010. Histology of the Blood by Paul Ehrlich and Adolf Lazarus. Translated by M. Myers. Section 2. Introduction. Definition of anemia. Clinical methods of investigation of the blood. In practical medicine, the term anemia has not quite the restricted sense that scientific investigation gives it. The former regards certain striking symptoms as characteristic of the anemic condition: pallor of the skin, a diminution of the normal redness of the mucous membranes of the eyes, lips, mouth, and pharynx. From the presence of these phenomena, anemia is diagnosed, and according to their greater or less intensity, conclusions are also drawn as to the degree of the poverty of the blood. It is evident from the first that a definition based on such a frequent and elementary chain of symptoms will bring into line much that is unconnected, and will perhaps omit what it should logically include. Indeed, a number of obscurities and contradictions is to be ascribed to this circumstance. The first task, therefore, of a scientific treatment of the anemic condition is carefully to define its extent. For this purpose the symptoms above mentioned are little suited, however great, in their proper place, their practical importance may be. Etymologically, the word anemia signifies a want of the normal quantity of blood. This may be general and affect the whole organism, or local and limited to a particular region or a single organ. The local anemias we can at once exclude from our consideration. A priori, the amount of blood may be subnormal in two senses, quantitative and qualitative. We may have a diminution of the amount of blood, oligemia. Deterioration of the quality of the blood may be quite independent of the amount of blood, and must primarily express itself in a diminution of the physiologically important constituents. Hence, we distinguish the following chief types of alteration of the blood: 1. Diminution of the amount of hemoglobin, oligochromemia, and 2. Diminution of the number of red blood corpuscles, oligocythemia. We regard as anemic all conditions of the blood where a diminution of the amount of hemoglobin can be recognized. In by far the greater number of cases, if not in all, oligemia and oligocythemia to a greater or lesser extent occur simultaneously. The most important methods of clinical hematology bear directly or indirectly on the recognition of these conditions. There is at present no method of estimation of the total quantity of the blood which can be used clinically. We rely to a certain extent on the observation of the already mentioned symptoms of redness or pallor of the skin and mucous membranes. To a large degree these depend upon the composition of the blood, and not upon the fullness of the peripheral vessels. If we take the latter as a measure of the total amount of blood, isolated vessels, visible to the naked eye, that is, those of the sclerotic, may be observed. Most suitable is the ophthalmoscopic examination of the width of the vessels at the back of the eye. Rehlmann has shown that in 60% of the cases of chronic anemia, in which the skin and mucous membranes are very white, there is hyperemia of the retina, which is evidence that in such cases the circulating blood is pale in color, but certainly not less in quantity than normally. The condition of the pulse is an important indication of diminution of the quantity of the blood, though only when it is marked. It presents a peculiar smallness and feebleness in all cases of severe oligemia. The bleeding from fresh skin punctures gives a further criterion of the quantity of blood, within certain limits, but is modified by changes in the coagulability of the blood. Anyone who has made frequent blood examinations will have observed that in this respect extraordinary variations occur. In some cases scarcely a drop of blood can be obtained, while in others the blood flows freely. One will not err in assuming in the former case a diminution of the quantity of the blood. The fullness of the peripheral vessels, however, is a sign of only relative value, for the amount of blood in the internal organs may be very different. The problem how to estimate exactly, if possible mathematically, the quantity of blood in the body has always been recognized as important, and its solution would constitute a real advance. The methods which have so far been proposed for clinical purposes originate from Takhanov. He suggested that one may estimate the quantity of blood by comparing the numbers of the red blood corpuscles before and after copious sweating. Apart from various theoretical considerations, this method is far too clumsy for practical purposes. Quincke has endeavored to calculate the amount of blood in cases of blood transfusion for therapeutic purposes. From the number of red blood corpuscles of the patient before and after blood transfusion, the amount of blood transfused and the number of corpuscles it contains, by a simple mathematical formula, the quantity of the blood of the patient can be estimated. But this method is only practicable in special cases and is open to several theoretical errors. First, it depends upon the relative number of red blood corpuscles in the blood, inasmuch as the transfusion of normal blood into normal blood, for example, would produce no alteration in the count. This consideration is enough to show that this proceeding can only be used in special cases. It has indeed been found that an increase of the red corpuscles per cubic millimeter occurs in persons with a very small number of red corpuscles who have been injected with normal blood. But it is very hazardous to try to estimate therefrom the volume of the pre-existing blood, since the act of transfusion undoubtedly is immediately followed by compensatory currents and alterations in the distribution of the blood. No property of the blood has been so exactly and frequently tested as the number of red corpuscles per cubic millimeter of blood. The convenience of the counting apparatus and the apparently absolute measure of the result have ensured for the methods of enumeration an early clinical application. At the present time the instruments of Thomas Zeiss or others similarly constructed are generally used, and we may assume that the principle on which they depend and the methods of their use are known. A number of fluids are used to dilute the blood, which on the whole fulfill the requirements of preserving the form and color of the red corpuscles, of preventing their fusing together, and of allowing them to settle rapidly. Of the better known solutions we will here mention Pacini's and Hayem's fluids. Pacini's solution: Hydrargyrum bichloratum 2 grams, Natrium chloratum 4 grams, Glycerin 26 grams, Aqua destillata 226 grams. Hayem's solution: Hydrargyrum bichloratum ½ gram, Natrium sulfuricum 5 grams, Natrium chloratum 1 gram, Aqua destillata 200 grams. For counting the white blood corpuscles the same instrument is generally used, but the blood is diluted 10 times instead of 100 times. It is advantageous to use a diluting fluid which destroys the red blood corpuscles, but which brings out the nuclei of the white corpuscles, so that the latter are more easily recognized. For this purpose the solution recommended by Thoma is the best, namely a 0.5% solution of acetic acid to which a trace of methyl violet has been added. Footnote: For the estimation of the numbers of white corpuscles relatively to the red and of the different kinds relatively to each other, see the section on the morphology. End footnote. The results of these methods of enumeration are sufficiently exact, as they have, according to the frequently confirmed observations of R. Thoma and I. F. Lyon, only a small error. In a count of 200 cells it is 5%, of 1,250 2%, of 5,000 1, and of 20,000 1/2%. There are certain factors in the practical application of these methods which in other directions influence the result unfavorably. It has been found by Cohnstein and Zuntz and others that the blood in the large vessels has a constant composition, but that in the small vessels and capillaries the formed elements may vary considerably in number, though the blood is in other respects normal. Thus, for example, in a one-sided paralytic, the capillary blood is different on the two sides, and congestion, cold, and so forth, raise the number of red blood corpuscles. Hence, for purposes of enumeration, the rule is to take blood only from those parts of the body which are free from accidental variation, to avoid all influences such as energetic rubbing or scrubbing, etc., which alter the circulation in the capillaries, to undertake the examination at such times when the number of red blood corpuscles is not influenced by taking of food or medicine. It is usual to take the blood from the tip of the finger, and only in exceptional cases, for example in edema of the finger, are other places chosen, such as the lobule of the ear or, in the case of children, the big toe. For the puncture, pointed needles or specially constructed instruments, open or shielded lancets, are unnecessary. We recommend a fine steel pen, of which one nib has been broken off. It is easily disinfected by heating to redness, and produces not a puncture, but what is more useful, a cut, from which blood freely flows without any great pressure. The literature dealing with the numbers of the red corpuscles in health is so large as to be quite unsurveyable. According to the new and complete compilation of Reinhardt and von Limbeck, the following figures, calculated roundly for cubic millimeters, may be taken as physiological. Men, maximum 7 million, minimum 4 million, average 5 million. Women, maximum 5,250,000, minimum 4,500,000, average 4,500,000. This difference between the sexes first makes its appearance at the time of puberty of the female. Up to the commencement of menstruation, the number of corpuscles in the female is in fact slightly higher than in the male, stelline. Apart from this, the time of life seems to cause a difference in the number of red corpuscles only insofar that in the newly born, polycythemia, up to 8.5 millions during the first days of life, is observed. E. Schiff. After the first occasion on which food is taken a decrease can be observed, and gradually, though by stages, the normal figure is reached in from 10 to 14 days. On the other hand, the oligocythemia here and there observed in old age, according to Schmalz, is not constant, and therefore cannot be regarded as a peculiarity of senility, but must be caused by subsidiary processes of various kinds, which come into play at this stage of life. The influence which the taking of food exercises on the number of the red blood corpuscles is to be ascribed to the taking in of water, and is so insignificant that the variations, in part at least, fall within the errors of the methods of enumeration. Other physiological factors: menstruation, that is, the single occurrence, pregnancy, lactation, do not alter the number of blood corpuscles to any appreciable extent. The numbers do not differ in arterial and venous blood. All these physiological variations in the number of the blood corpuscles are dependent, according to Cohnstein and Zuntz, on vasomotor influences. Stimuli which narrow the peripheral vessels locally diminish the number of red blood corpuscles. Excitation of the vasodilators brings about the opposite effect. Hence it follows that the normal variations of the number contained in a unit of space are merely the expressions of an altered distribution of the red elements within the circulation, and are quite independent of the reproduction and decay of the cells. Climatic conditions apparently exercise a great influence over the number of corpuscles. This fact is important for physiology, pathology, and therapeutics, and has come to the front especially in the last few years, since Violt's researches in the heights of the Cordilleras. As his researches, as well as those of Mercier, Egger, Wolf, Köppe, von Jarontowski, and Schröder, Mischer, Kündig, and others, show, the number of red blood corpuscles in a healthy man, with a normal average of 5 million per cubic millimeter, begins to rise immediately after reaching a height considerably above the sea level. With a rise proceeding by stages, a new average figure is reached in 10 to 14 days, considerably larger than the old one, and indeed the greater the difference in level between the former and the latter places, the greater is the difference in this figure. Healthy persons born and bred at these heights have an average of red corpuscles which is considerably above the mean, and which indeed as a rule is somewhat greater than in those who are acclimatized or only temporarily living at these elevations. The following small table gives an idea of the degree to which the number of blood corpuscles may vary at higher altitudes from the average of 5 millions. Author von Jaruntowski. Locality Görbersdorf. 561 meters above sea level. Increase of 800,000. Author Wolfgang Köppe. Locality Reiboldsgrün. 700 meters above sea level. Increase of 1 million. Author Egger. Locality Arosa. 1,800 meters above sea level. Increase of 2 million. Author Viot. Locality Cordilleras. 4,392 meters above sea level. Increase of 3 million. Exactly the opposite process is to be observed when a person accustomed to a high altitude reaches a lower one. Under these conditions, the correspondingly lower physiological average is produced. These interesting processes have given rise to various interpretations and hypotheses. On the one hand, the diminished oxygen tension in the upper air was regarded as the immediate cause of the increase of red blood corpuscles. Miescher, particularly, has described the want of oxygen as a specific stimulus to the production of erythrocytes. Apart from the physiological improbability of such a rapid and comprehensive fresh production, one must further dissent from this interpretation, since the histological appearance of the blood gives it no support. Köppe, who has specially directed part of his researches to the morphological phenomena produced during acclimatization to high altitudes, has shown that in the increase of the number of red corpuscles, two mutually independent and distinct processes are to be distinguished. He observed that, although the number of red corpuscles was raised so soon as a few hours after arrival at Reiboldsgrün, numerous poikilocytes and microcytes make their appearance at the same time. The initial increase is therefore to be explained by budding and division of the red corpuscles already present in the circulating blood. Köppe sees in this process, borrowing Ehrlich's conception of poikilocytosis, a physiological adaptation to the lower atmospheric pressure and the resulting greater difficulty of oxygen absorption. The impediment to the function of the hemoglobin is to a certain extent compensated, since the stock of hemoglobin possesses a larger surface, and so is capable of increased respiration. So also the remarkable fact may be readily understood that the sudden rise of the number of corpuscles is not at first accompanied by a rise of the quantity of hemoglobin, or of the total volume of the red blood corpuscles. These values are first increased when the second process, an increased fresh production of normal red discs, takes place, which naturally requires for its development a longer time. The poikilocytes and microcytes then vanish, according to the extent of the reproduction, and finally a blood is formed which is characterized by an increased number of red corpuscles, and a corresponding rise in the quantity of hemoglobin, and in the percentage volume of the corpuscles. Other authors infer a relative and not an absolute increase in the number of red corpuscles. E. Grawitz, for example, has expressed the opinion that the raised count of corpuscles may be explained chiefly by increased concentration of the blood, due to the greater loss of water from the body at these altitudes. The blood of laboratory animals, which Grawitz allowed to live in correspondingly rarefied air, underwent similar changes. Von Limbeck, as well as Schumburg and Zuntz, object to this explanation on the ground that if loss of water caused such considerable elevations in the number, we should observe a corresponding diminution in the body weight, which is by no means the case. Schumburg and Zuntz also regard the increase of red blood corpuscles in the higher mountains as relative only, but explain it by an altered distribution of the corpuscular elements within the vascular system. In their earlier work, Kornstein and Zuntz had already established that the number of corpuscles in the capillary blood varies with the width of the vessels and the rate of flow in them. If one reflects how multifarious are the merely physiological influences at the bottom of which these two factors lie, one will not interpret alterations in the number of the red corpuscles without bearing them in mind. In residence at high altitudes, various factors bring about alterations in the width of the vessels and in the circulation. Amongst these are the intenser light, fülles, the lowering of temperature, increased muscular exertion, raised respiratory activity. Doubtless, therefore, without either production of microcytes or production de novo, the number of red corpuscles in capillary blood may undergo considerable variations. The opposition in which, as mentioned above, the views of Grawitz, Zuntz, and Schumberg stand to those of the first mentioned authors, finds its solution in the fact that the cause of altered distribution of the blood and of loss of water play a large part in the sudden changes. The longer the sojourn, however, at these great elevations, the more insignificant they become. Viot. We think therefore that from the material before us we may draw the conclusion that after long residence in elevated districts the number of red blood corpuscles is absolutely raised. The therapeutic importance of this influence is obvious. Besides high altitudes, the influence of the tropics on the composition of the blood, and especially on the number of corpuscles, has also been tested. Eichmann as well as Glogner found no deviation from the normal, although the almost constant pallor of the European in the tropics points in that direction. Here also, changes in the distribution occurring without qualitative changes of the blood seem chiefly concerned. The same reliance cannot be placed on inferences based on the results of the Thomas-Zeiss and similar counting methods for anemic as for normal blood, in which generally speaking all the red cells are of the same size and contain the same amount of hemoglobin. In the former, the red corpuscles, as we shall show later, differ considerably one from another. On the one hand, forms poor in hemoglobin, on the other, very small forms occur, which by the wet method of counting cannot even be seen. Apart even from these extreme forms, 1,000 red blood corpuscles of anemic blood are not physiologically equivalent to the same number of normal blood corpuscles. Hence, the necessity of closely correlating the result of the count of red blood corpuscles with the hemoglobinometric and histological values. The first figure only, given apart from the latter, is often misleading, especially in pathological cases. It is therefore occasionally desirable to supplement the data of the count by the estimation of the size of the red blood corpuscles individually. This is effected by direct measurement with the ocular micrometer, and can be performed on wet, see below, as well as on dry preparations, though the latter in general are to be preferred on account of their far greater convenience. Nevertheless, the carrying out of this method requires particular care. One can easily see that in normal blood the red corpuscles appear smaller in the thicker than they do in the thinner layers of the dry preparation. We may explain this difference as follows. In the thick layers the red discs float in plasma before drying, whilst in the thinner parts they are fastened to the glass by a capillary layer. Desiccation occurs here nearly instantaneously, and starts from the periphery of the disc, so that an alteration in the shape or size is impossible. On the contrary, the process of drying in the thicker portions proceeds more slowly, and is therefore accompanied by a shrinking of the discs. Even in healthy persons, small differences in the individual discs are shown by this method. The physiological average of the diameter of the greater surface is, according to Lache, Hayem, Schumann, and others, 8.5 micrometers for men and women, maximum 9 micrometers, minimum 6.5 micrometers. In anemic blood, the differences between the individual elements become greater, so that to obtain the average value, the maxima, minima, and mean of a large number of cells, chosen at random, are ascertained. But with a high degree of inequality of the discs, this microscopical measurement loses all scientific value. However valuable the knowledge of the absolute number may be for a judgment on the course of the illness, It gives us no information about the amount of hemoglobin in the blood, which is the decisive measure for the degree of the anemia. A number of clinical methods are in use for this estimation. First direct, such as the colorimetric estimation of the amount of hemoglobin. Secondly indirect, such as the determination of the specific gravity or of the volume of the red corpuscles, and perhaps also the estimation of the dry substance of the total blood. Among the direct methods for hemoglobin estimation, which aim at the measurement of the depth of color of the blood, we wish first to mention one, which though it lays no claim to great clinical accuracy, has often done us good service as a rapid indicator at the bedside. A little blood is caught on a piece of linen or filter paper and allowed to distribute itself in a thin layer. In this manner one can recognize the difference between the color of anemic and of healthy blood more clearly than in the drop as it comes from the finger prick. After a few trials one can in this way draw conclusions as to the degree of the existing anemia. Could this simple method, which is so convenient, which can be carried out at the time of consultation, come more into vogue, it alone would contribute to the decline of the favorite stop-gap diagnosis, anemia. For neurasthenic patients also, who so often fancy themselves anemic and in addition look so, a demonstratio ad oculos, such as this, is often sufficient to persuade them of the contrary. Of the instruments for measuring the depth of color of the blood, the double pipette of Hoppe-Seyler is quite the most delicate. A solution of carbonic oxide hemoglobin, accurately titrated, serves as the standard of comparison. The reliable preparation and conservation of the normal solution is however attended with such difficulties that this method is not clinically available. In the last few years, Langemeister, a pupil of Kühnes, has invented a method for colorimetric purposes, also applicable to hemoglobin estimations. The instrument depends on the principle that from the thickness of the layer in which the solution to be tested has the same color intensity as a normal solution, the amount of color can be calculated. As a normal solution, Langemeister uses a glycerin solution of methemoglobin prepared from pig's blood. To our knowledge, this method has not yet been applied clinically. Its introduction would be valuable, for in practice we must at present be content with methods that are less exact, in which colored glass or a stable colored solution serves as a measure for the depth of color of the blood. There are a number of instruments of this kind, of which the hemometer of Fleischl and amongst others, the hemoglobinometer of Gowers, distinguished by its low price, are specially used for clinical purposes. Both instruments give the percentage of the hemoglobin of normal blood, which the blood examined contains, and are sufficiently exact in their results for practical purposes and for relative values, although errors up to 10% and over occur with unpracticed observers. See K. H. Meyer. Quite recently, Biernacki has raised the objection to the colorimetric methods of the quantitative estimation of hemoglobin that the depth of color of the blood is dependent not only on the quantity of hemoglobin, but also on the color of the plasma and the greater or less amount of proteid in the blood. These errors are quite inconsiderable for the above-mentioned instruments, since here the blood is so highly diluted with water that the possible original differences are thereby reduced to zero. Among the methods for indirect hemoglobin estimation, that of calculation from the amount of iron in the blood appears to be quite exact, since hemoglobin possesses a constant quantity of iron of 0.42%. This calculation may be allowed in all cases for normal blood, for here there is a really exact proportion between the amounts of hemoglobin and of iron. Recently, A. Jolles has described an apparatus for quantitative estimation of the iron of the blood, called a ferrometer, which renders possible an accurate valuation of the iron in small amounts of blood. However, for pathological cases, this method of hemoglobin estimation from the iron present is not to be recommended. For if one tests the blood of an anemic patient under the microscope for iron, one finds the iron reaction in numerous red blood corpuscles. This means the presence of iron which is not a normal constituent of hemoglobin. Other iron may be contained in the morphological elements, including the white corpuscles, as a combination of proteid with iron which is not directly recognizable. It is further known that in anæmias the amount of iron of all organs is greatly raised (Quincke), apparently often the result of a raised destruction of hemoglobin (waste iron, spodogenous iron). In many cases, too, it should be borne in mind that the administration of iron increases the amount of iron in the blood and organs. From these considerations we see how unreliable in pathological cases is the calculation of the amount of hemoglobin from the amount of iron. We have been particularly led to these observations by the work of Biernacki, since the procedure of inferring the amount of hemoglobin from the amount of iron has led to really remarkable conclusions. For example, amongst other things, he found the iron in 2 cases of mild and one of severe chlorosis quite normal. He concludes that chlorosis and other anæmias show no diminution, but even a relative increase of hemoglobin, but that other proteids of the blood, on the contrary, are reduced. These difficult iron estimates stand out very sharply from the results of other authors, and could only be accepted after the most careful confirmation. But the above analysis shows that in any case the far-reaching conclusions which Biernacki has attached to his results are insecure. For these questions especially, complete estimations with the aid of the ferrometer of Arjoles are to be desired. Great importance has always been attached to the investigation of the specific gravity of the blood, since the density of the blood affords a measure of the number of corpuscles and of their hemoglobin equivalent. It is easy to collect observations, as in the last few years 2 methods have come into use, which require only a small quantity of material, and do not appear to be too complicated for practical clinical purposes. One of these has been worked out by R. Schmaltz, in which small amounts of blood are exactly weighted in capillary glass tubes, the capillary pycnometric method. The other is A. Hammerschlag's, in which, by a variation of a principle which was first invented by Fano, that mixture of chloroform and benzol is ascertained in which the blood to be examined floats, that is, which possesses exactly the specific gravity of the blood. Footnote: in Roy's method, mixtures of glycerin and water are used. By means of a curved pipette the drop of blood is brought into the fluid and its immediate motion observed. Lazarus Barlow has modified this method. He employs mixtures of gum and water, and instead of several tubes only one, and into this the mixtures are introduced, those of higher specific gravity being naturally at the bottom. The alternate layers are colored and remain distinguishable for several hours. End of footnote. According to the researches of these authors and numerous others who have used their own methods, the specific gravity of the total blood is physiologically 1058 to 1062, or on the average 1056 in women. The specific gravity of the serum amounts to 1029 to 1032, on the average 1030. From which it at once follows that the red corpuscles must be the chief cause of the great weight of the blood. If their number diminishes, or their number remaining constant, they lose in hemoglobin or in volume, the specific gravity would be correspondingly lowered. We should therefore expect a low specific gravity in all anemic conditions. Similarly, with an increased number of corpuscles and a high hemoglobin equivalent, an increase in the density of the total blood makes its appearance. Hammerschlag has found in a large number of experiments that the relation between the specific gravity and the amount of hemoglobin is much closer than between the specific gravity and the number of corpuscles. The former, in fact, is so constant that it may be represented by a table. Specific gravity 1033 to 1035. Quantity of hemoglobin, by Fleischl's method, 25 to 30%. Specific gravity 1035 to 1038, 30 to 35% of hemoglobin. Specific gravity 1038 to 1040, 35 to 40% of hemoglobin. Specific gravity 1040 to 1045, 40 to 45% of hemoglobin. Specific gravity 1045 to 1048, 45 to 55% of hemoglobin. Specific gravity 1048 to 1050, 55 to 65% of hemoglobin. Specific gravity 1050 to 1053, 65 to 70% of hemoglobin. Specific gravity 1053 to 1055, 70 to 75% of hemoglobin. Specific gravity 1055 to 1057, 75 to 85% of hemoglobin. Specific gravity 1057 to 1060, 85 to 95% of hemoglobin. In a paper which has quite recently appeared, Diabella has investigated these relations very thoroughly, and his results partly correct and partly confirm those of Hammerschlag. Diabella found from his comparative estimations that differences of 10% hemoglobin, Fleischl, correspond in general to differences of 4.46 per thousand in the specific gravity, Hammerschlag's method. Nevertheless, with the same amount of hemoglobin, differences up to 13.5 per thousand are to be observed, and these departures are greater the richer the blood in hemoglobin. Regular differences exist between men and women. The latter have, with the same amount of hemoglobin, a specific gravity lower by 2 to 2.5. Should a parallelism between the number of red blood corpuscles and the amount of hemoglobin be considerably disturbed, the influence of the stroma of the red discs on the specific gravity of the blood will then be recognizable. Diabella calculates that with the same amount of hemoglobin in two blood testings, the stroma may affect differences of 3 to 5 per thousand in the specific gravity. Hence, the estimation of the specific gravity is often sufficient for the determination of the relative amount of hemoglobin of a blood. It is only in cases of nephritis and in circulatory disturbances and in leukemia that the relations between specific gravity and quantity of hemoglobin are too much masked by other influences. The physiological variations which the specific gravity undergoes under the influence of the taking in and excretion of fluid do not exceed 0.003 Schmaltz. From what has been said, it follows that all variations must correspond with similarly occurring variations in the factors that underlie the amount of hemoglobin and the number of corpuscles. More recent authors, in particular Hammerschlag, von Jaksch, von Limbeck, Biernacki, Dunin, E. Gravitz, A. Löwy, have avoided an omission of many earlier investigations, for besides the estimation of the specific gravity of the total blood, they have carried out that of one at least of its constituents, either of the corpuscles or of the serum. The red blood corpuscles have consistently shown themselves as almost exclusively concerned with variations in the specific gravity of the total blood, partly by variations in number or changes in their distribution, partly by their chemical instability, loss of water and absorption of water, and variations in the amount of iron. The plasma of the blood, on the contrary, and there is no essential difference between plasma and serum, Hammerschlag, is much more constant. Even in severe pathological conditions, in which the total blood has become much lighter, the serum preserves its physiological constitution or undergoes but relatively slight variations in consistence. Considerable diminutions in the specific gravity of the serum are much less frequently observed in primary blood diseases than in chronic kidney diseases and disturbances of the circulation. E. Gravitz has lately recorded that in certain anemias, especially post-hemorrhagic and those following inanition, the specific gravity of the serum undergoes perceptible diminutions. Footnote: In conditions of shock experimentally produced, the specific gravity of the total blood is increased, that of the plasma, however, is diminished. Roy and Cobbett. End of footnote. There are still, therefore, many contradictions in these results, and it is evidently necessary in a scientific investigation always to give the specific gravity of the serum and of the corpuscles, in addition to that of the total blood. A method closely related to the estimation of the specific gravity is the direct estimation of the dried substance of the total blood, hygrometry, the clinical introduction of which we owe to Stinzig and Gumprecht. This method is really supplementary to those so far mentioned, and like them can be carried out with the small amounts of blood obtainable at the bedside without difficulty. Small quantities of blood are received in weighted glass vessels, which are then weighed, dried at 65 to 70 degrees Celsius for 24 hours, and then weighed again. The figures so obtained for the dried substance have a certain independent importance, for they do not run quite parallel with those of the specific gravity, amount of hemoglobin or number of corpuscles. The normal values are for men 21.26%, for women 19.8%. A further procedure for obtaining indirect evidence of the amount of hemoglobin is the determination of the volume of blood corpuscles in 100 parts of total blood. For this estimation a method is desirable which allows of the separation of the corpuscles from plasma in blood that is as far as possible unaltered. The older methods do not fulfill this requirement, since they recommend either defibrillation of the blood, quite impossible with the quantities of blood which are generally clinically available, or keeping it fluid by the addition of sodium oxalate or other substances which prevent coagulation. The separation of the two constituents can be effected by simply allowing the blood to settle, or with the centrifugal machine specially constructed for the blood by Blix-Hedin and Gärtner, hematocrit. For these methods various diluting fluids are used, such as the physiological saline solution, 2.5% of potassium bichromate, and many others. According to H. Köppe, they are not indifferent as far as the volume of the red blood corpuscles is concerned, and a solution which does not affect the cells must be previously ascertained for each specimen of blood. For this reason attention may be called to the proceeding of M. Hertz, in which the clotting of the blood in the pipette is prevented by rendering the walls absolutely smooth by the application of cod liver oil. Köppe has slightly varied this method. He fills his handily constructed pipette, very carefully cleaned, with cedar wood oil and sucks up the blood, as it comes from the finger prick into the filled pipette. The blood displaces the oil, and as it only comes into contact with perfectly smooth surfaces, it remains fluid. By means of a centrifugal machine, of which he has constructed a very convenient variation, the oil as the lighter body is completely removed from the blood, and the plasma is also separated from the corpuscles. 3 sharp defined layers are then visible, the layer of oil above, the plasma layer, and the layer of the red blood corpuscles. Inasmuch as the apparatus is calibrated, the relation between the volumes of the plasma and corpuscles can be read off. No microscopical alterations in the corpuscles are to be observed. Though this procedure seems very difficult of execution, it is nevertheless the only one which has really advanced clinical pathology. The results of Köppe, not as yet very numerous, give the total volume of the red corpuscles as 51.1 to 54.8%, an average of 52.6%. M. and L. Bleibtreu have endeavoured indirectly to ascertain the relation of the volume of the corpuscles to that of the plasma. Mixtures of blood with physiological saline solution in various proportions are made, in each the amount of nitrogen in the fluid which is left after the corpuscles have settled is estimated. With the aid of quantities so obtained, they calculate mathematically the volume of the serum and corpuscles respectively. Apart from the fact that a dilution with salt solution is also here involved, this method is too complicated and requires amounts of blood too large for clinical purposes. Th. Pfeiffer has tried to introduce it clinically in suitable cases, but has not so far succeeded in obtaining definite results. That, however, the relations between the relative volume of the red corpuscles and quantity of hemoglobin are by no means constant is well shown by conditions, for example the acute anemias, in which an acute swelling of the individual red discs occurs, m Hz, but without a corresponding increase in hemoglobin. The same conclusion results from recent observations of von Limbeck that in catheteral jaundice a considerable increase of volume of the red blood corpuscles comes to pass under the influence of the salts of the bile acids. As we have several times insisted, the quantity of hemoglobin affords the most important measure of the severity of an anemic condition. Those methods which neither directly nor indirectly give an indication of the amount of hemoglobin are only so far of interest that they possibly afford an elucidation of the special pathogenesis of blood diseases in particular cases. To these belong the estimation of the alkalinity of the blood, which in spite of extended observations has not yet obtained importance in the pathology of the blood. A value to which perhaps attention will be more directed than it has up to the present time by clinicians is the rate of coagulation of the blood, for which comparative results may be obtained by Wright's handy apparatus, the coagulometer. In certain conditions, particularly in acute exanthematous, and in the various forms of the hemorrhagic diathesis, the clotting time is distinctly increased, or indeed clotting may remain in abeyance. Occasionally a distinct acceleration in the clotting compared with the normal may be observed. Wright has further ascertained in his excellent researches that the clotting time can be influenced by drugs, calcium chloride, carbonic acid rays, citric acid, alcohol, and increased respiration diminish the clotting power of the blood. Recently, Hayem has repeatedly called attention to a condition that is probably closely connected with the coagulability of the blood. Although coagulation has set in, the separation of the serum from the clot occurs only very slightly or not at all. Hayem asserts that he has found such blood in purpura hemorrhagica, anemia perniciosa protopatica, malarial cachexia, and some infectious diseases. For such observations large amounts of blood are needed, which are clinically not frequently available. Certain precautions must be observed, as has been ascertained in the preparation of diphtheria serum, so that the yield of serum may be the largest possible. Among these, that the blood should be received in longish vessels, which must be especially carefully cleaned, and free from all traces of fat. If the blood clot does not spontaneously retract, it must be freed from the side of the glass with a flat instrument like a paper knife, without injuring it. If no clot occurs in the cold, a result may perhaps follow at blood temperature. In spite, however, of all artifices and all care, it is here and there, under pathological conditions, impossible to obtain even a trace of serum from considerable amounts of blood. In a horse, for example, which was immunized against diphtheria and had before yielded an unusually large quantity of serum, Ehrlich was able to obtain from 22 kilograms of blood scarcely 100 cubic centimeters of serum when the animal was bled on account of a tetanus infection. Perhaps a larger role is to be allotted in the diseases of the blood to these conditions. Hayem already turns the incomplete production of serum to account for distinguishing protopathic pernicious anema from other severe anemic conditions. A bad prognosis, too, may be made when, for example, in cachitic states this phenomenon is to be observed. A few methods still remain to be mentioned which test the resistance of the red blood corpuscles to external injuries of various kinds. Landois, Hamburger, and von Limbeck ascertained, for instance, the degree of concentration of a salt solution in which the red corpuscles are preserved, isotonic concentration, Hamburger, and those which cause an exit of the hemoglobin from the stroma. The erythrocytes are the more resistant, the weaker the concentration which leaves them still uninjured. Lake attests the red blood corpuscles as regards their resistance to the electric discharge from a Leyden jar, and measures it by the number of discharges up to which the blood in question remains uninjured. Clinical observation has not yet gained much by these methods. So much only is certain, that in certain diseases, anemia, hemoglobinuria, and after many intoxications, the resistance, as measured by the methods above indicated, is considerably lowered. End of section 2.
Section 3 of the Histology of the Blood. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by John Coos. Histology of the Blood by Paul Ehrlich and Adolf Lazarus. Translated by M. Myers. Section 3. A. Methods of investigation. A glance at the history of the microscopy of the blood shows that it falls into two periods. In the first, which is especially distinguished by the work of Virchow and Max Schultze, a quantity of positive knowledge was quickly won, and the different forms of anemia were recognized. But close upon this followed a standstill, which lasted for some decades, the cause of which lay in the circumstance that observers confined themselves to the examination of fresh blood. What, in fact, was to be seen with the aid of this simple method, these distinguished observers had quickly exhausted. That these methods were inadequate is best shown by the history of leukocytosis, which, after the precedent of Virchow, was in general referred to an increased production on the part of the lymphatic glands, and further by the imperfect distinction between leukocytosis and incipient leukemia, which was drawn almost exclusively from purely numerical estimations. It was only after Ehrlich had introduced the new methods of investigation by means of stained, dry preparations that the histology of the blood received the impulse for its second period. We owe to them the exact distinction between the different kinds of white blood corpuscles, a rational definition of leukemia, polynuclear leukocytosis, and the knowledge of the appearances of degeneration and regeneration of the red blood corpuscles, and of their degeneration in hemoglobinemic conditions. The same process, then, has gone on in the microscopy of the blood that we see in other branches of normal and pathological histology. By advances in method, advances in knowledge, full of importance result. It is therefore little comprehensible that an author quite recently should recommend a reversion to the old methods, and emphatically announce that he has managed to make a diagnosis in all cases, with the examination of fresh blood. At the present time, after the most important points have been cleared up by new methods, in the large majority of cases this is not an astonishing achievement. For any difficult case, for instance, the early recognition of malignant lymphoma, certain rare forms of anemia, etc., as the experienced know, the dry, stained preparation is indispensable. The object of examining the blood is certainly not to make a rapid diagnosis, but to investigate exactly the individual details of the blood picture. Today, we can only take the standpoint that everything is to be seen in fresh specimens, apart from the quite unimportant rouleau formation and the amoeboid movements, can be seen equally well, and indeed much better, in a stained preparation, and that there are several important details which are only made visible in the latter and never in wet preparations. As regards the purely technical side of the equation, the examination of stained dry specimens is far more convenient than that of fresh, for it leaves us quite independent of time and place. We can keep the dried blood with few precautions for months at a time, before proceeding to further microscopic treatment, and the examination of the preparation may last as long as required, and can be repeated at any time. On the contrary, the examination of the wet preparation is only possible at the bedside, and must be conducted within so short a time, on account of the changeability of the blood, clotting, destruction of white corpuscles, and so forth, that a searching investigation cannot be undertaken. In addition, the preparation and staining of dried blood specimens is amongst the simplest and most convenient of the methods of clinical histology. In the interest of its wider dissemination, it will be justifiable to describe it in more detail. We must also mention here the use of dry preparation, in the estimation of the important relation between the number of the red and of the white corpuscles, and also of the relative numbers of different kinds of white blood corpuscles. For this purpose, faultless specimens, specially regularly spread, are indispensable. Quadratic ocular diaphragms, Ehrlich are requisite, which form a series, so that the sides of the squares are as 1 to 2 to 3, all the way to 10. The fields, therefore, as 1 to 4 to 9, all the way to 100. The eyepiece made by Lights after Ehrlich's directions is more convenient, in which, by a handy device, definite square fractions of the field can be obtained. The enumeration is made as follows. The white blood corpuscles are first counted in any desired field with the diaphragm number 10, that is, with the area of 100. Without changing the field, the diagram 1, which only leaves free a 100th part of this area, is now put in, and the red corpuscles are counted. The field is then changed at random, and the red corpuscles counted in a portion of the area which represents the 100th of that of the white. About 100 such counts are to be made in a specimen. The average of the red corpuscles is then multiplied by 100, and so placed in proportion with the sum of the white. If the white corpuscles are very numerous, so that counting each one in a large field is inconvenient, smaller sections of the eyepiece, 81, 64, 49, etc., may be taken. The important estimation of the percentage relation of the various forms of leukocytes is effected by the simple typing of several hundred cells, a count which for the practiced observer is completed in less than a quarter of an hour. A. Preparation of the dry specimen. To obtain unexceptionable preparations, cover slips of particular quality are necessary. They should not be thicker than 0.08 to 0.10 millimeters. The glass must not be brittle or faulty, and must in this thickness easily allow of considerable bending without breaking. Every unevenness of the slip renders it useless for our purposes. The glasses must previously be particularly carefully cleaned and all fat removed. It is generally sufficient to allow the slips to remain in ether for about half an hour, not covering one another. Each one still wet with ether is then wiped with soft, not coarse, linen rag or with tissue paper. The slips now are put into alcohol for a few minutes, are dried in the same manner as from the ether, and are kept ready for use in a dust-tight watch-glass. Bearing in mind that these cover slips are not cut out from a flat piece but from the surface of a sphere, it is evident that only with glasses thus prepared can it be expected that a capillary space should form between two of them, in which the blood spreads easily. For, with the smallest unevenness or brittleness of the glass, it is an impossibility for the one to fit every bend of the other, and it is only then that the slips can be drawn away from one another without using a force which breaks them. To avoid fresh soiling of the cover slips, and above all the contact of the blood with the moisture coming from the finger, the cover glass is held with forceps. Footnote: Klon and Müller, Berlin, supply these after Ehrlich's directions. End footnote. To receive the blood. We recommend for the undercover glass a clamp forceps A, with broad, smooth blades. The ends may be covered with leather or blotting paper for a distance of about 1/2 inch. For the other cover slip, a very light spring forceps B with smooth blades, sharp at the tips, is used, with which a cover glass can be easily picked up from a flat surface. The lower slip is now fixed by one edge in the clamp forceps, and held ready in the left hand. The right hand applies the upper glass with the forceps B to the drop of blood as it exudes from the puncture, and takes it up without retouching the finger itself. The forceps B is then quickly brought to A, and the slip with the little drop of blood allowed to fall lightly on the other. In glasses of the right quality, the drop distributes itself spontaneously in a completely regular capillary layer. With 2 fingers of the right hand on the edge of the upper glass, it is now carefully pulled from the lower, which remains fixed in the clamp, without pressing or lifting. Frequently only one, the lower, shows a regular layer, but occasionally both are available for examination. During the desiccation in the air, generally complete in 10 to 30 seconds, the preparations must naturally be protected from any dampness, for example, the breath of the patient. The extent of surface which is covered depends on the size of the drop. The smaller the latter, the smaller the surface over which it has to be spread. Large drops are quite useless, for with them the one cover glass swims on the other instead of adhering to it. Although a written description of these manipulations makes the method seem rather intricate, yet but little practice is required to obtain an easy and sure mastery over it. We have felt compelled to describe the method minutely, since preparations so often come under our notice which, although made by scientific men who pursue hematological investigations, are only to be described as technically completely inadequate. The specimens so obtained, after they are completely dried in the air, should be kept between layers of filter paper in well-closed vessels till further treatment. In important cases, preparations of which it is desirable to keep for some considerable time, some of the specimens should be kept from atmospheric influences by covering them with a layer of paraffin. The paraffin must be removed by toluol before proceeding further. The preparations must naturally be kept in the dark. B. Fixation of the dry specimen. All methods of staining available for the blood require the fixing of the proteids of the blood. A general formula cannot be given, since the intensity of the fixation must be regulated in accordance with the kind of stain that is chosen. Relatively slight degrees of hardening suffice for staining in simple watery solutions. For example, in the triacid fluid, and can be attained by a short and not too intense action of several regions. For other methods, in which solutions that are strongly acid or alkaline are employed, it is however necessary to fix the structure much more strongly. But here, too, an excess as well as an insufficiency must be guarded against. It is easy with the few staining fluids that are in use to ascertain the optimum for each. The following means of fixation are employed. 1. Dry heat. A simple plate of copper on a stand is used, under one end of which burns a Bunsen flame. After some time, a certain constancy in the temperature of the plate is reached. The part nearest to the flame is hottest. That farther away is cooler. By dropping water, toluol, xylol, etc. onto it, one can fairly easily ascertain that point of the plate which has reached the boiling temperature of the particular fluid. Far more convenient is Victor Meyer's apparatus, used by chemists. This consists of a copper boiler, modified for our purpose, with a roof of thin copper plate, perforated for the opening of the vapor tube. Small quantities of toluol are allowed to boil for a few minutes in the boiler, and the copper plate soon reaches the temperature of 107 degrees to 110 degrees. For the ordinary staining reagents in watery fluids, it is enough to place the air-dried preparation at about 110 degrees Celsius for 1/2 to 2 minutes. For differential staining mixtures, for instance the eosin-aurantia nigrosin mixture, a time of 2 hours is necessary, or higher temperatures must be employed. 2. Chemical means. A. To obtain a good triacid stain, the preparations may be hardened, according to Nikiforov, in a mixture of absolute alcohol and ether of equal parts for 2 hours. The beauty of specimens fixed by heat is, however, not quite fully reached by this method. B. Absolute alcohol fixes dried specimens in 5 minutes sufficiently to stain them subsequently with Chenzinsky's fluid or hemotoxylin eosin solution. It is an advantage in many cases, especially when rapid investigation is required, to boil the dried preparation in a test tube in absolute alcohol for 1 minute. C. Formalin in 1% alcoholic solution was first used by Bernario for fixing blood preparations. The fixation is complete in 1 minute, and the granulations can be demonstrated. Bernario recommends this method of fixing, especially for the hemotoxylin eosin staining. These methods are described as the most suitable for blood investigation in general. For special purposes, for instance, the demonstration of mitoses, blood platelets, etc., other hardening reagents may be used with advantage. Sublimate, osmic acid, Fleming's fluid, and so forth. Gamma. Staining of the dry specimen. Staining methods may be classified according to the purpose to which they are adapted. We use first those which are suitable for a simple general view. For this, it is sufficient to use such solutions as stain hemoglobin and nuclei simultaneously. Hemotoxylin eosin, hemotoxylin orange. Occasionally, a stain is desirable which only brings out, but in a characteristic manner, a special kind of cell, example, the eosinophils, mast cells, or bacteria. Single staining is attained on the principle of maximal decoloration. C.P.E. Westphal. Finally, we have panoptic staining, that is, by methods which bring out, as characteristically as possible, the greatest number of elements. Although we must use high magnifications with these stains, we are compensated by a knowledge of the blood condition that cannot be reached in any other way. A double stain is generally insufficient, and at least 3 different dyes are used. Successive staining was formerly used for this purpose, but everyone who has used this method knows how difficult it is to get constant results, however careful one may be in the concentration and time of action of the stain. Simultaneous staining offers undoubted and important advantages. As there is much obscurity with regard to the principle on which it rests, we may here shortly explain the theory of simultaneous staining. We will begin with the simplest example, the use of picrocarmine, a mixture of neutral ammonium carmine and ammonium picrate. In a tissue rich in protoplasm, carmine alone stains diffusively, though the nuclei are clearly brought out. But if we add an equally concentrated solution of ammonium picrate, the staining gains extraordinarily in distinctness, inasmuch as now certain parts are pure yellow, others pure red. The best known example is the staining of muscle with picrocarmine, by which the muscle substance appears pure yellow, the nuclei pure red. If, however, instead of ammonium picrate, we add another nitro dye, which contains more nitro groups than picric acid, for example the ammonium salt of hexanitro diphenylamine, the carmine stain is completely abolished. All parts stain in the pure aurantia color. The explanation of this phenomenon is obvious. Myosin has a greater affinity for ammonium picrate than for the carmine salt, and therefore in a mixture of the two combines with the yellow dye. Owing to this combination, it is not now in a condition to chemically fix even carmine. Further, the nuclei have a great affinity for the carmine, and therefore stain pure red in this process. If, however, nitro dyes be added to the carmine solution, which have an affinity for all tissues, and also for the nuclei, the sphere of action of the carmine becomes continually smaller, and finally, by the addition of the most powerful nitro body, the hexanitro compound is completely abolished. Connective tissue and bone substance, however, behave differently with the picrocarmine mixture, inasmuch as here the diffuse stain depends exclusively on the concentration of the carmine, and is quite uninfluenced by the addition of the chemical antidote. This staining can only be limited by dilution, but not by the addition of opposed dyes. We must look upon the latter kind of tissue stain not as a chemical combination, but as a mechanical attraction of the stain on the part of the tissue. We may also say chemical stains are to be recognized by the fact that they react to chemical antidotes, mechanical stains to physical influences. Of course, always assuming that purely neutral solutions are employed, and that all additions, which alter the chemical relation of the tissues, such as alkalis and acids, or which raise or limit the affinity of the dye for the tissues, are avoided. A further consequence of this view is that all successive double staining may be serviceably replaced by simultaneous multiple staining, if the chemical nature of the staining process is settled. In contradistinction, in all double stains, which can only be effected by successive staining, mechanical factors are concerned. In the staining of the dry blood specimen, purely chemical staining processes are concerned, and therefore the polychromatic combination stain is possible in all cases. The following combinations are possible for the blood. 1. Combine the staining with acid dyes. The best known example is the eosin aurantia nigrosin mixture, in which the hemoglobin takes on an orange, the nuclei a black, and the acidophil granulations a red hue. 2. Mixtures of basic dyes. It is possible straightaway to make mixtures consisting of 2 basic dyes. As specially suitable, we must mention fuchsin, methyl green, methyl violet, methylene blue. On the other hand, mixtures of 3 bases are fairly difficult to prepare, and the quantitative relations of the constituents must be exactly observed. For such mixtures, fuchsin, Bismarck brown, chrome green may be used. 3. Neutral mixtures. These have played an important part in general histology from the time that they were first introduced by Ehrlich into the histology of the blood up to the present day, and deserve before all others a full consideration. Neutral staining rests on the fact that nearly all basic dyes, i.e. salts of the dye bases, for instance, rosanilin acetate, form combinations with acid dyes, i.e. salts of the dye acids, for instance, ammonium picrate, which are to be regarded as neutral dyes, such as rosanilin picrate. Their employment offers considerable difficulties as they are very imperfectly soluble in water. A practical application of them was first possible after Ehrlich had ascertained that certain series of neutral dyes are easily soluble in excess of the acid dye. And so the preparation of solutions of the required strength, readily kept, was made possible. Among the basic dyes which are suitable for this purpose are those particularly which contain the ammonium group, especially methyl green, methylene blue, amethyst violet, tetraethyl safranochloride, and to a certain extent pyronin and rhodamin also. In contradistinction to these, the members of the triphenylmethan series, such as fuchsin, methyl violet, Bismarck brown, phosphine, indazine, are in general less suited for the purpose, with the exception of methyl green already mentioned. The acid dyes specially suited for the production of soluble neutral stains are the easily soluble salts of the polysulfonyl acids. The salts of the carbonyl acids and other acid phenol dyes are but little suitable, and least of all the nitro dyes. Specially to be mentioned among the acid dye series are those which can be used for the preparation of the neutral mixtures: orange G, acid fuchsin, narcine, and easy soluble yellow dye, the sodium salt of sulfonylic acid, hydrozo beta naphthalsulfonic acid. If a solution of methyl green be allowed to fall drop by drop into a solution of an acid dye, for instance orange G, a coarse precipitate first results, which dissolves completely on the first addition of the orange. No more orange should be added than is necessary for a complete solution. This is the type of a simple neutral staining fluid. Chemically, the above mentioned example may be thus explained. In this mixture, all 3 basic groups of the methyl green are united with the acid dye, so that we have produced a triacid compound of methyl green. Simple neutral mixtures, which have one constituent in common, may be combined together straight away. This is very important for triple staining, which can only be attained by mixing together 2 simple neutral mixtures, each consisting of 2 components. A chemical decomposition need not be feared. We thus get mixtures containing 3 and more colors. Theoretically, there are 2 possibilities for such outcomes. 1. staining mixtures of one acid and two basic dyes. Example, orange, amethyst, methyl green, narcine, pyronin, methyl green, narcine, pyronin, methylene blue. 2. Staining mixtures of two acids and one base. In particular, the mixture to be described later in detail of orange G, acid fuchsin, methyl green, further narcine, acid fuchsin, methyl green, and the corresponding combinations with methylene blue and amethyst violet may be mentioned. The importance of these neutral staining solutions lies in the fact that they pick out definite substances, which would not be demonstrated by the individual components, and which we therefore call neutrophil. Elements which have an affinity for basic dyes, such as nuclear substances, stain in these neutral mixtures purely in the color of the basic dye. Acidophil elements in that of one of the two acid dyes, whilst those portions of tissue which from their constitution have an equal affinity for acid and basic dyes attract the neutral compound as such and therefore stain in the mixed color. The eosine methylene blue mixtures are exceptional insofar that it is possible with them, for a short time at least, to preserve active solutions in which, with an excess of basic methylene blue, enough eosine is dissolved for both to come into play. A drawback, however, of such mixtures is that in them precipitates are very easily produced, which render the preparation quite useless. This danger is particularly great in freshly prepared solutions. In solutions such as Chenzinsky's, which can be kept active for a longer time, it is less. Hence, fresh solutions stain far more intensely and more variously than older ones, and are therefore used in special cases. See page 46. If the stain is successful, the appearances are very instructive. Nuclei are blue, hemoglobin red, neutrophil, granulation violet, acidophil pure red, mast cell granulation deep blue, forming one of the most beautiful microscopic pictures. For practical purposes, besides the iodine and iodine eosine solution described below, see page 46, the following are especially used. Hematoxylin solution with eosin or orange G. Eosin crystal 0.5. Hematoxylin 2.0. Alcohol ABS. AQU DEST. Glycerin AA 100. Glacial acetic acid 10.0. Alum in excess. The fluid must stand for some weeks. The preparations, fixed in absolute alcohol, or by short heating, stain in from half an hour to 2 hours. The hemoglobin and eosinophil granules are red. The nuclei stain in the color of hematoxylin. The solution must be very carefully washed off. 2. In the practical application of the triacid fluid, particular care must be taken, as M. Heidenhain first showed, that the dyes are chemically pure. Footnote: at M. Heidenhain's instigation, the Aniline Dye Company of Berlin have prepared the three dyes in the crystalline form. End footnote. Formerly, granules, apparently basophil, were frequently observed in the white blood corpuscles, particularly in the region of the nucleus. They were not recognized, even by practiced observers, e.g. Neusser, as artificial, but were regarded as preformed, and were described as paranuclear forms. Since the employment of pure dyes, these appearances, whose meaning for a long time puzzled us, are but seldom seen. Saturated watery solutions of the three dyes are first prepared and cleared by standing for some considerable time. The following mixture is now made: 13 to 14 cc's orange G solution, 6 to 7 cc acid fuchsin solution, 15 cc AQU-DEST, 15 cc alcohol, 12.5 cc methyl green, 10 cc alcohol, 10 cc glycerin. These fluids are measured in the above mentioned order with the same measuring glass, and from the addition of methyl green onwards the fluid is thoroughly shaken. The solution can be used at once and keeps indefinitely. The staining of the blood specimen in triacid requires only a little fixation. CP page 35. The stain is completed in 5 minutes at most. The nuclei are greenish, the red blood corpuscles orange, the acidophil granulation copper red, the neutrophil violet. The mast cells stand out by negative staining as peculiar bright, almost white cells with nuclei of a pale green color. The triacid stain is very convenient. It is much to be recommended for good general preparations. It is indispensable in all cases where the study of the neutrophil granulations is concerned. 3. Basic double staining. Saturated, watery methyl green solution is mixed with alcoholic fuchsin. The stain, which only requires a small fixation, is completed in a few minutes, and colors the nuclei green, the red blood corpuscles red, the protoplasm of the leukocytes fuchsin color. It is therefore especially suited for demonstration preparations of lymphatic leukemia. Eosin methylene blue mixtures, for example Chenzinsky's fluid, concentrated watery methylene blue solution 40 cc, 1/2% eosin solution in 70% alcohol 20 cc, aqua DEST 40 cc. This fluid is fairly stable, but must always be filtered before use. It only requires a fixation of the specimen for 5 minutes in absolute alcohol. The staining takes 6 to 24 hours in air-tight watch glasses at blood temperature. The nuclei and the mast cell granulations stain deep blue, malaria plasmodia light sky blue, red corpuscles, and eosinophil granules a fine red. The solution is particularly suited for the study of the nuclei, the baso and eosinophil granulations, and it is used by preference for anemic blood and also for lymphatic leukemia. 5. 10 cc of a 1% watery eosin solution with 8 cc methylol and 10 cc of a saturated water solution of methylene blue are mixed and used at once. See page 41. Time of staining 1, at most 2 minutes. The staining is characteristic only in preparations very carefully fixed by heat. The mast cell granulations are stained pure blue, the eosinophil red, the neutrophil in mixed color. Jenner's stain consists of a solution in methyl alcohol of the precipitate formed by adding eosin to methylene blue. Grubler's water-soluble eosin yellow 1.25% AA watery. Medicinal methylene blue 1% solutions. Precipitate allowed to stand 24 hours and then dried at 55 degrees. It is then made up to 1/2% in methyl alcohol, Merck. The stain may be obtained from R. Canthek, 18, Berners Street, London, ready for use. It is exceedingly sensitive to acids and alkalis. Fixation is effected by heat, time of staining 1 to 4 minutes. Before we pass to the histology of the blood, two important methods may be described, for which the dried blood preparations is employed directly, without previous fixation. 1. Recognition of glycogen in the blood. 2. The microscopic test of the distribution of the alkali of the blood. 1. Recognition of the glycogen in blood. This may be effected in two ways. The original procedure consisted in putting the preparation into a drop of thick, cleared, iodine India rubber solution under the microscope, as had been already recommended by Ehrlich for the recognition of glycogen. The following method is still better. The preparation is placed in a closed vessel containing iodine crystals. Within a few minutes it takes on a dark brown color, and is then mounted in a saturated levulose solution whose index of refraction is very high. To preserve these specimens, they must be surrounded with some kind of cover glass cement. By the use of better methods, the red blood corpuscles which have taken on the iodine stain stand out, without having undergone any morphological change. The white blood corpuscles are only slightly stained. All parts containing glycogen, on the contrary, whether the glycogen be in the white blood corpuscles or extracellular, are characterized by a beautiful mahogany brown color. The second modification of this method is specially to be recommended on account of the strong clearing action of the levulose syrup. In using the iodine India rubber solution, a small quantity of glycogen in the cells may escape observation owing to the opaqueness of the India rubber, and occasionally, too, by the separate staining of the same. The second, more delicate method is for this reason recommended in the investigation of cases of diabetes and other diseases. 2. The microscopic test of the distribution of alkali in the blood. These methods rest on a procedure of Mylius for the estimation of the amount of alkali in glass. Iodine eosine is a red compound easily soluble in water, but is not soluble in ether, chloroform, or toluol. But the free colored acid, which is precipitated by acidifying solutions of the salt,
is very sparingly soluble in water.
It is, on the contrary, very easily soluble in organic solvents, so that by shaking it completely passes over into an ethereal solution which becomes yellow. If this solution be allowed to fall on glass, on which deposits of alkali have been formed by decomposition, they stand out in a fine red color as the result of the production of the deeply colored salt. In its application to the blood, of course, the vessels used for staining, as well as the cover glasses, must be cleaned from all adhering traces of alkali by means of acids. The dry specimen is thrown directly after its preparation into a glass vessel containing a chloroform or chloroform toluol solution of free iodine eosine. In a short time it becomes dark red. It is then quickly transferred to another vessel containing pure chloroform, which is once more changed, and the preparation still wet from the chloroform is then mounted in Canada balsam. In such preparations the morphological elements have preserved their shape completely. The plasma shows a distinct red color, while the red corpuscles have taken up no color. The protoplasm of the white corpuscles is red. The nuclei appear as spaces, because unstained negative nuclear staining. The disintegrated corpuscles and the fibrin which is produced show an intense red stain. These stains are peculiarly instructive, and show many details which are not visible in other methods. The study of these preparations is really of the highest value, since they allow the products of manipulation of the dry preparation and every error of production to stand out in the most reliable manner, and so render possible a kind of automatic control. The scientific value of this method lies in the fact that it throws light on the distribution of the alkali in the individual elements of the blood. It appears that free alkali reacting in iodine eosine is not present in the nuclei. These must therefore have a neutral or an acid reaction. On the contrary, the protoplasm of the leukocytes is always alkaline, and the largest amount of alkali is held by the protoplasm of the lymphocytes. We call particular attention in this connection to the strong alkalinity of the blood platelets. End of section 3. A. Methods of investigation. Recording by John Thomas Kazmarski or John Thomas Kuz at www.validateyourlife.com.